All right, everyone, let's take a quick look at the kind of big ideas from today's windmill lab. The first one is we've got our net torque equation. Net torque equals I rotational inertia times alpha rotational acceleration. So I is how much rotational inertia, which is how much an object resists rotationally accelerating. We can see that net torque equals I alpha is similar to Newton's second law, which is net force equals mass times acceleration, where mass is inertia and I is rotational inertia. So rotational inertia, with the symbols capital I, and the units are kilograms times meters squared. So let's do kind of a comparison and contrasting between mass and rotational inertia. Okay, so mass and inertia are the same thing. The more inertia an object has, the harder it is to accelerate the object. Similarly, the more rotational inertia an object has, the harder it is to rotationally accelerate the object. But the difference is here, there's only one way to change inertia, and the way we do it is to change the mass of the object. But there's two ways that we can change rotational inertia, and we can do one by changing the mass of the object, more mass, more rotational inertia. But we can also change how the mass is distributed relative to the axis of rotation. The further the mass is distributed away from the axis of rotation, the larger the rotational inertia. And so that's why we saw in our windmill lab that the windmill where the mass was further outside on the spokes had larger rotational inertia and therefore resisted accelerating more. So it had a smaller alpha or rotational acceleration. One thing we didn't quite get to today is this. How do we calculate rotational inertia? So if we've got like a group of objects that are connected together, you would need to add up all their individual rotational inertia values to get the total. So like we're going to look at this example in a minute, pretend like this is our windmill, and there's lots of pieces to this windmill. We've got this center disc, we've got 4 spokes, and then we've got 4 outside masses, okay? And we're going to pretend like those outside masses are all the way on the edge for our example. Well, to get the total rotational inertia of this windmill, we'd have to add up the disc's rotational inertia, the 4 spokes, and the 4 outside masses to get the total rotational inertia. You also need to know that the equation for the rotational inertia of a point mass, that's like one spot that's rotating around a pivot point, is mass of that object times its distance from the axis of rotation squared. So, for example, we would consider these masses, these outside masses, to be point masses because they're this distance away from the axis of rotation. We can consider them to all have their mass be at one point. But we couldn't do that with a disk because it's kind of like evenly distributed across this distance away from the axis of rotation. And we certainly couldn't do it for these metal rods because they're also distributed different distances away from the axis of rotation. But it's easy to visualize that these like outside masses could all be like at one point because they're all basically the same distance away from the axis of rotation. So, like I said, to find the rotational inertia of the windmill as a whole, we've got to take the rotational inertia of the center disc, 4 times the rotational inertia of one of these metal rods, and 4 times the rotational inertia of an outside mass. So the equation for a disk, the rotational inertia of a disk, is 1/2 mr squared. So 1/2 times the mass of the disk times its radius squared. This disk has a radius of about 5 centimeters or 0.05 meters. Gives us this for the rotational inertia of the center disk. The metal rods, the equation for the rotational inertia of the metal rod is 1/3 ml squared, where L is the length of the object. So we've got the mass of the rods is about 100 grams or 0.1 kilograms, and the length of these rods is about 30 centimeters. So we get 0.003 kilograms times meter squared. And the rotational inertia of the outside masses, these are point masses. So we can use mr squared for them. The mass, they are also 100 grams, and they are at the end of the rod, so they are at 30 centimeters or 0.3 meters. So when we multiply that out, we get 0.009 kilograms times meter squared. And so to get the rotational inertia of the windmill, we just add these all up. So the center disk plus 4 times the rotational inertia of the metal rod plus 4 times the rotational inertia of the outside mass. We get that the rotational of the windmill as a whole is 0.049 kilograms times meter squared. There you go. I hope that helps you with your homework tonight. Thanks for watching.